Hello everyone, I am Charana at Data Valley working as an AI engineer. Today we are talking about give your AI agent a memory boost. So, what does this mean? Here each part holds a specific technical meaning. Okay, here give your means here this emphasizes the practical hands-on nature of what we are learning. Okay, here we are not just discussing the theoretical concepts, we're also talking about how we can implement and enhance our own AI agents. That's why I mentioned here your give your AI agent, as you know, technical term AI agent, and a memory boost. Memory refers to the capacity of an agent, okay, which retain and recall the information over time. That is known as a memory. Next, boost in the sense overcoming the limitations of LLMs. Okay, so don't worry, we'll see what this means technically, theoretically in next slides. So let's begin. Yes, understanding memory in AI. This diagram illustrates this architecture of an AI agent, right? If you see on this left icon, I placed a human, but which is represents this human which interacts with the AI agent. From this human, it is pointing to that agent, right? And if you see agent have a prompt template, LLM memory and tools. The prompt template means uh, which we include predefined instructions or rules that are used to structure the input which we are giving to the LLM, which is termed as an prompt. Okay, next, from the agent, it also pointing this planning or reasoning, right? So this planning or reasoning, this means agent sends the user prompt to that LLM, and that LLM output is sent back to the agent again. That's why it is pointing both sides. Here planning and reasoning is done by LLM. Next, and it is also moving to memory and tools. Here, I have mentioned actions. Actions is done using tools. Means LLM decides to perform a specific action, and that is by executing a specific tool. And last, which I mentioned, store or retrieve. That is labeled with a store and retrieve, which connects with the memory. This is a highlight of our discussion today. So that memories could be in any past conversations, or what is the facts learned during the task, or any user preferences also, or any data from external documents. They all are considered as a memory here. So this is a simple architecture of an AI agent. Next, what we will cover today. In our today's video, we'll cover this why memory is essential for AI agents. What if there is no memory for an AI agent? We'll discuss on that one. And what are the memory types we have? We'll discuss on that one. And next, we are connecting this topic to how to store that memory, how to make that memory. That concept comes under how vector stores work. Okay, by creating these embeddings, how they are storing the data in the memory of an agent. Next, adding memory to an agent. Using some coding samples, I'll show you how to add a memory to an agent. And next, we'll move to limitations and what are the limitations of this memory in agents also. These we are going to cover today. Let's begin. Why memory is essential for AI agents? Here, when we talk about some limitations, what if there is no memory for agents? Once there is no memory, no data from the internet, then that LLM also become a stateless. Each prompt, each time will you give an prompt, it become an independently processed only, right? So it doesn't inherently remember the previous turns in our conversations. That is the first point. Stateless LLMs. Next thing is limited context window. That means generally context window in the sense there will be a maximum number of tokens in the sense words or characters which we are sending to that through context window. Those number of characters are processed at once. Okay, once this information will go to these LLM, means out of this window, then LLM forgets it. Okay, that makes difficult for long conversations to remember. Okay, that is limited context window if there is no memory. Next, we get only generic responses. Means without memory of these past interactions or any user preferences, it will get a lag or just answers which are without user preferences and very generic or generalized answers because of lacking any personalization. Okay. Next, repetitive actions. So if there is no memory, it will repeatedly one. Even if I said about myself in one conversation, it will repetitively ask again and again because there is no memory. It is not storing anything. That makes this repetitive actions. These are our limitations without memory. Next, the power of memory. We'll talk about this power of memory is context preservation. Yes, it will maintain the long running conversations and personalization. Personalization in the sense, if a user give any user preferences, I want this kind of movies, and I will save that in a Netflix, and it will only give that my references only. That is termed as personalization. Next, learning and adaptation. It will learn to that preferences. Okay, she is liking only action related movies only. Then it will retrieve only that thing related movies only. That is learning and it will adapt itself. Okay, next, multi-turn reasoning. Multi-turn in the sense, this allows agents to build on previous steps. Okay, even if you change the topic in between when you are chatting with the chat GPT, even if you change the topic in between, when you ask the previous thing, it will retrieve that one. So here multi-turn reasoning is happening with memory. Next, efficiency. Efficiency in this, it will simply if we don't give or it will process independently, it will ask for the repeated questions, right? For our preferences. So this efficient with memory, it will avoid this re-asking or reprocessing the information. That is one of the advantage. So these are the essentials for AI agents. So that's why memory is very essential. Next, types of memory. When comes to these types of memory, now we have learned that memory is essential. Okay, fine. Now, how to store that memory? Is it like a human brain? How much, or if yes, how much data we can store? Based upon that one, it is categorized into two types: short-term memory and long-term memory. For this short-term memory, this is an LLM's immediate working memory. Okay, which is, see, if you see in this diagram, it is represented by the conversation between this human message and AI message. Okay, it is limited to only one context window. Okay, I mean, it is only certain amount of recent conversations only fit in this window. Once it reaches a checkpoint that indicates that this is a short term context and can be saved and summarized to be added and to be added to this long term memory. That is the use of this checkpoint. It can remember only limited memory. When comes to this long term memory, this is for a vast amounts of information like a knowledge base or full conversation history. This can be stored and retrieved whenever it is needed. Why? Because here this is implemented, long term memory is implementing vector stores. Okay, we'll see what are the vector stores in our next slides. These vector stores hold embeddings of the information. It means it will store that information. I'll tell you what are embeddings also. So it has a much knowledge than, I mean, much, it can able to store much larger amounts of data than short term memory. So it can remember things across many interactions and sessions. How it will remember, we will see. Why? Because it has a vector stores, which I mentioned here, stores. And next, this large language model, LLM, is a brain, right? So it just works with the short-term memory and it can access long-term memory by sending a query. Okay, and it will retrieve the relevant information from that. How that will be, we will see in our next slides. So here if you see what is this store, store is a vector database, you can term it also vector database also. So how these vector stores works, I'm sorry, yeah. How these vector stores works and the power of embeddings, we will see here. uh, so generally, if you talk in a low level point of view, for the storage, we'll use hard drive and clouds nowadays, and server and USB stick. These are the technologies we have used. Here, the database vector storage is a database which is designed to store high dimensional data. As a day by day, we are making things and storing large amount of data and various types of data. From the data which includes the integers, numbers, strings, that strings in the sense text, videos, images, and images to videos. So when we are changing these images to videos here, there will be an increase in dimensional. So dimension of data is going to be increased here. That's why we need a large amount of space to store these kinds of data. That's why nowadays, to make an AI agent, first we are looking for a long term memory so that it will retrieve the information from that. Okay. First point is what it is doing is text to embeddings. For suppose whatever the data is we have, it will convert that text to embeddings. As I mentioned here, text, we can take an image or video or whatever numerical data also. It will, whatever the data, it will convert into embeddings. So what are embeddings means? These are numerical vectors. Numerical vectors means a list of numbers. For suppose just a number, that what is that numbers indicates means semantic meaning. For suppose if we have a word king, what is the meaning of that king is stored in the form of numerical vectors. Those numerical vectors are called as embeddings. So for every word, it will store one numerical vector. So these embeddings transform that text to these list of numbers, what we are calling as numerical vectors. So how we are converting this data to these numerical vectors is we have a specialized AI model is known as embedding model. Okay, that is what is embedding model in sense? It is a neural network. which takes a piece of text and outputs some vector. So each number in that vector represent any kind of, we call it as a feature, or if we take image as an input, it can be a pixel value. If you take an text, it may be a its meaning. So it will capture the meaning and relationship between those words also. Okay, so here the magic part is embedding model is trained in such that a way, okay, which will capture that a meaning of words. For suppose we have a word called king. It might be close to queen also. Okay, so embedding for king and embedding for queen is nearby. Those vectors in the dimensional space will be a very close to each other. If we take another strings, like for suppose table, chair, these embeddings of for table and chair will be far away from the king, because those are not related to king, right, directly. Queen is somewhat related to king. That will be, so that the in numerical space these vectors will be close to each other. Okay, for suppose man is also related to king, right? So if we take woman is also close to queen. So if we see here, embeddings captures not just meaning but the relation. It will capture the relations, and it will store these embeddings vector which are having same meaning together, which have same meaning together will be stored nearby. That's why it is very easy to retrieve information. Okay, that is text to, that is how the text is converted to embeddings. Next, storing these embeddings in vector store. For suppose, think like this vector store in the sense, so will get a many thousands and millions of embeddings from the text. Imagine a vector store as like a digital library. But now, instead of organizing those books by title, it organizes them by meaning, because it will capture the semantic meaning of words. Okay, so this is a special kind of database designed to hold these number of list of numbers. Those are called embeddings, and to quickly find that list of numbers that are similar to given one. These vector stories, you can easily retrieve the similar searches, which is similar. You can easily retrieve that one. Okay, that is how we will store that in a vector store. And if that vector, after storing in that vector store or vector database, how we will retrieve that one, that information. Okay, all these embeddings are storing in vector store. How we will retrieve is simply, for an agent to find the right information in that vast memory. First, what we'll do when we ask a question or a query to an AI agent, first it needs to understand what is the meaning of the your question. Then the first thing agent does is it take your question and convert into embeddings, then the using some embedding model. Okay, we have many models to convert these embeddings. When AI agent actively looks for this relevant information in this long term memory, that is vector store, and it will retrieve the similar search. So once your question is transformed into embedding, the vector store swings into some action that performs similarity search. Okay, this is highly efficient process where the vector store compares this embeddings of your question with all embeddings of the text. which is stored in the vector store. Then the outcome of this similarity search is termed as text chunks. Okay, any related information where you are getting from the vector store as identified as a most relevant to your question. Here it is making a similarity search. That is termed as nowadays a popular thing is RAG, retrieval augment generation. This is a technique which is used to retrieve that similarity search from the memory. Okay, so how it will connecting that memory is after performing okay, it will compare your question embeddings with all the embeddings present in the vectors. Then the agent now has original question and few relevant pieces of text from the long term memory. The crucial step is now it will retrieve these text chunks and inject them directly to this LLM's prompt. If we see in our previous videos, I have shown you how the question we are inserting and how we can also insert the answer to it also. So after this agent retrieving the text chunks, it will directly inject the LLM's prompt. This means LLM's short-term context window is now contains not just a question but actual information where which who gave that information agent is found in that memory and it will give to LLMs. With this prompt, these LLMs becomes an incredible powerful. Now LLMs has an prompt what to do, and these agent gave what is the information which is stored in the vector database. That's why LLM made powerful. So it uses this natural language understanding, NLP, and reasoning capabilities also. That's why the primary benefit of this RAG is that LLMs doesn't have to remember everything from the initial training data. Instead, it understands how to ask. Simply it will ask agent. Agent will retrieve the information from the long term memory. What is long term memory here? Vector store from specific date to up to date. And what is the factual information? Then it will retrieve. So because of these answers, here the LLM is grounded in real data, right? Which also reduces hallucination, which we discussed in our previous videos also, in our last video. So that makes these agents scalable because we are adding more knowledge to the vector store. Okay, without straining this LLM. Without straining LLM, we are simply adding a more data to the vector store. Next, let have a how this works technically. We will see. Okay, adding memory to an agent in LangChain. Okay, I'm using LangChain, which is an open source, so that we will. It makes easy to understand how this works in a real time. Okay, up to now we have seen just a conceptual thing, I mean, theory part. Now we will consider some scenario here. What is that is Q and A, questioning and answering agent with document memory, suppose. Okay, so our goal is to build an agent that can answer questions about a specific set of documents. What are the documents? For suppose here I mentioned our company policies and product manuals. Suppose every company has every predefined policies, right? We'll give that one or we'll store that one in a vector store. Okay. Now we are using the tools. What are the tools? Our agent will use a retrieval tool to take that query from our vector store. Next, LLMs. LLM will act as a reasoning engine, right? All together comes an agent. So first thing what we'll do is load documents. Okay. Oh, sorry. Load document. Whatever the documents we have. For suppose we have uh, inserted all our policies or instructions or company policies into a text document. We imagine just we are uploading that text file. Here I have mentioned, if you see, I have mentioned here policy.txt. This is the file which we have a company policies. Okay, this is the file we want to store in our vector database. So first the line is from LangChain underscore community document loaders and import text loader. So we are importing the text loader from the LangChain community. Okay. Next, we are creating here text loader followed by our document. So we are creating an instance for this text loader. Why instance? Because that is a class which we are importing from the LangChain community. Text loader is a class. We are creating an instance for that and telling it to load the content from the file. Okay. What is a file? Policy.txt. And where we are storing that file in a loader variable. We are storing that in a loader variable. Next, document is equal to loader dot to loader. Here we are executing this loader variable after reading this policy.txt file, and it will converting these contents into a list of document objects. Okay, though which are then stored in a documents variable. Again, we are creating a documents variable and we are storing that one list of document objects. Okay, next. After loading documents, whatever the documents we have, after loading a number of documents, we need to split the documents. That is called as chunks. Chunking. Okay, means breaking a large documents into smaller or manageable chunks for a better retrieval. Okay. So in the same again first line, we are importing character text splitter from the LangChain itself. Okay, this character text splitter is a class which is designed to break the large text into a smaller and more manageable pieces. Okay, based on those characters. Here, if you observe, we have mentioned this chunk size is 1000 and chunk overlap is 200. That means yes, we are creating chunks up to 1000 characters and allowing of overlap 200 characters between that consecutive chunks. Okay, for suppose we are in our context window, it will have a maximum number of limited tokens, right? So we are creating chunks of up to 1000 characters and allowing 200 characters in between that chunks as a main context. Okay, that is the meaning of that one. So this line text, we are storing that one in a text splitter. So this line applies this splitter to load our documents and resulting in a list of small chunks. Why? Because why small chunks is to easier for our vector stores to process and retrieve. If we give a large amount of data directly to the vector store, it will get a strain on our CPU or GPU what we are using. That's why we'll use or we'll split that text into chunks. Okay. Next, and we are storing that one in chunks variable. Yes, we are storing the chunks variable. Next, create embeddings and store in vector store. Okay. After creating these chunks, now what we are doing is we have to choose an embedding model. I have told you just before. there will be an embedding model which converts these text to numerical vectors. Here, Hugging Face or OpenAI have these embedding models. Okay, uh, to load that one, here we are importing OpenAI embeddings from the LAN chain. Okay, and Chroma. This is also an which is used to initialize an vector store. Means adding that document chunks and their embeddings to the vector database. We use this one. Okay, Chroma is to initialize the vector store, and we are importing the embedding model from OpenAI embeddings. We can have a different various models also to convert these things. Next, as of now we are importing this OpenAI embeddings. That is a class from LangChain, which allows us to use this OpenAI's models, which generate embeddings from the text. Okay, next. From LangChain committee, we are also importing this Chrome. And this is also an open source vector which can store and retrieve those embeddings. Next, we are storing embedding in that embeddings variable. We are creating an object of OpenAI embeddings. Okay. So this is next. This is an vector store. Yes, this is a crucial step here. If we see, it takes our chunks. So in chroma dot from documents, in that parameters we are passing chunks and embeddings are the two parameters we are passing. So it takes our chunks of the text with the corresponding embeddings. This will populate the chroma vector store, means it will add chunks to the vector store. So if you see, for suppose here the chunk will be a queen, and it will have a parallel embeddings. Okay, so we are converting the actual embedding with the vector store and numerical vectors and storing in vector store. Okay, that is the meaning of this, converting the passing the chunks and corresponding embeddings to the store. Next, integrate that vector stores and return tool. Okay, up to here we have seen how to inject the data into the store. Next, what if we want to retrieve? That's why we are here creating a retrieve from the vector store. If you see in our previous videos also, sir have told about making this tools. Here we are defining a custom tool for that, for an agent. Okay, here we have tool class, which is used to define a specific action or capability that an AI agent can perform. This converts our vector store object into retrieval object. Okay, this tool is which available in langchain.agents, which is specially designed to fetch the relevant documents based on a query. Next, we are storing a vector store dot as retriever function and in retriever variable, right? Retrieve. Okay. Hmm. And next, we are using this retrieval tool. What we are making here is tool, and in that tool we are passing three parameters: name, function, and description. So name is the document search, means this is the name that LLM will use to refer this tool. Okay, if you have seen this yesterday's video where we have given how LLM we will given or it will retrieve tool's name also. Okay, this will refer to the tool when it decide to look up for an information. We are passing the tool name. And next, function retriever dot get relevant documents. Okay, this specifies the function that will be called when this tool is used. Okay, and from that it will take the information relevant document as an that function output. So this is a function and tool name. Description. It will also read the description useful for answering questions about internal document. So this is a natural language explanation for the LLM. It will guide the LLM on when to use this tool. This is an also important. Yes, LLM will read this description. It is important to add a description when you are passing this tool. Okay. Next, in tool is equals to we are passing a retrieval underscore tool. This create a list of all tools of our agent has access. Whatever that we give a tool to an agent. Okay, it will add all those in the list. In this case, it just only we are attaching as a document search tool only, right? So only the one tool it is added in a list. Next, build the agent. So how we are building an agent? LLMs plus we have tools plus memory. So combining all these and of course the React prompt template also. Now see if you are saying we are importing agent executor and create a React agent from the land chain and open chat open AI, or and if you want you can use any other LLMs also. Okay, as of now I took this one from the land chain. Next, we will initialize our language model. So if you see here in the parentheses, I have mentioned GPT-4 turbo model. Okay, setting up the temperature to 0 to get more deterministic responses. Okay, just I'm initializing that model and I'm storing that one in a LLM variable. Okay, next, combining these LLMs and list of tools like our document search and then prompt. Okay, all this in we are combining in that create underscore react underscore agent, and we are storing that in an agent variable. Next, this agent executor will be responsible for running this agent's logic by passing all these agent tool and LLM prompt. And also mention here verbose is equals to true. This brings the agent's internal thoughts and actions during execution. Okay. So this is how we built an agent, or all together it will start working. Next, query the agent. So the last 10 step, right? So if we ask the agent a question which we requires, it will retrieve the information from the long-term memory which we have created. Okay, simply here the line which I mentioned that will runs the agent with the specific query that we are passing here is what is the company's policy on remote work. Okay, the agent will then use these its LLM and tools including this retrieval tool also to formulate an answer. Okay, so this is the last which we are using query the agent. Next, expected agent flow. Now we will have a complete we will see overview of what is happening. Okay, just we made a kind of chunks and we have seen, right? Now we will see the complete agent flow. First one is thought. What is the thought? I need to find information about remote work policy. I should use the document tool search. It will think. Agent will first have a thought. Then it will do okay to use the document search tool. The action is to open that document search. Yes or no? To open that one, open in the sense that is a function, right? So what is the input for the function? We'll give remote work policy. We because in the question we asked what's the company's policy on remote work, right? So that's why if you see here the action input is remote work policy. And in observation, we got relevant text chunks about remote work policy from that vector store. What is the information which is related to remote work policy? Here, what I told is which are the similar to these each embedding that will be placed together so that it will be easy to retrieve the information. Here it will be very easy to get the information which is related to remote work policy. Next, what we have is thought I have retrieved the relevant policy. Once it get the embeddings, it is having that, oh yes, I got a retrieved relevant policy and I can now answer the question. And the final answer. This summarizes the policy based on this retrieved text. This is a top view of agent flow. How backend is related, that up to now what we see is the kind of backend. Okay. So this is complete agent, expected agent flow. Next, we have a cheat sheet which I have made. This one, what are the steps for our vector store setup? This will be an important thing. Okay. Just go through the same what we have discussed. Next, even we have such a very specialized vector store, still we have some limitations for this. Okay, what is that one is cost. So storing that such a large vector database can significantly go to the storage cost also. And we are using these external models, right? Or vector database services which can be lead to an API cost. We didn't build a OpenAI embedding right? We don't know how they are implemented a embedding model. We are just using those APIs. Okay, that's why it also gives to APIs cost. It will be very limited. Next, latency. What is latency is here for retrieving information from that vector store, which adds an step to an agent's loop, right? Reasoning loop. So for real-time applications, this can introduce some delays also. Okay, adding an another step to it. Generally, Python is if you use tools and LLMs, that will be a little bit slower sometimes. But here, adding a vector store that also may have a delays. Okay, so optimizing the speed, we have using Fascias is also one vector store, and indexing strategy is also there. That is also a crucial thing. And next we have a relevance, that is quality of retrieval. For suppose if the embedding model is poor, for suppose, or if chunking strategy is not that efficient, then this agent might retrieve irrelevant information also. Yes or no? That will be a loss for us. Next, security and privacy. Yes, storing such kind of sensitive user data and information in our memory systems of these vector stores. There might be an complicant with the data privacy also. Okay. Next, complexity of memory management. So deciding what to store, deciding when to retrieve, and deciding how to update that also. So these are strategies of handling this conflict information in memory. So we have that will be we have complexity a little bit. Okay. Next is scalability. When it comes to this scalability, these vector stores are designed for scaling, managing, and updating them. But truly like dynamic knowledges based on this, which are very complex. I mean, storing such a high dimensional data in our knowledge base is a little bit complex. So these are few limitations. But still, many things are going on, and most of the people are still using this as per their use cases, right? And yes, here is the conclusion, which I am ending this topic. Here, what we talk about today is a memory. Okay, the key, which is truly intelligent agents. So, understanding why it is crucial, we have seen why it is essential, how to store the memory, how to retrieve that one, and what are the limitations also. And the most important concept in AI agents, vector databases, which is backbone for long-term memory. Okay, this is enabling these agents to access the information. We have seen that thing. And stay tuned for next videos. We'll continue our journey in our foundations of agentic AI. Okay, and keep learning how we will create this agent, can learn and improve over time. Okay, don't stop learning, keep learning. And thank you. Bye.